In this video, we're going to consider the case where we have a point moment applied to a structure. So the structure we're going to consider is a simply supported beam. We have pin support at A on the left-hand side, a roller support at B on the right-hand side, and we have a point moment of 30 kilonewton meters applied in the clockwise direction. So as with all of the shear force bending moment problems we consider, the first thing we do is calculate the reactions. And we'll draw a quick free body diagram of the entire structure. So we have a vertical reaction force at A, RAY, a vertical reaction force at B, we'll call RBY, and this point moment of 30 kilonewton meters in the center, and then the dimensions 3 meters and 3 meters. For this problem, I'm going to start by taking moments about point A. So taking moments about point A, RAY acts through that position, so it has no lever arm, but I have the 30 kilonewton meters, but it's going in a clockwise direction, so I'm choosing that to be negative. And then I have RBY multiplied by the lever arm of 6 meters that's going in an anti-clockwise direction, which I'm choosing to be positive. And for equilibrium, the sum of those moments must be equal to 0. So I can rearrange this equation now in terms of RBY, and you get that RBY equals the minus 30 taken to the right hand side becomes plus 30, divide by the 6, and so RBY equals 5 kilonewtons. Now I'm going to take the sum of the forces in the y direction. So sum of the forces in the y direction, I have RAY plus RBY must be equal to 0, and I have a known value for RBY, and substituting that in gets me that RAY equals minus 5 kilonewtons, and that's in a downwards direction. So now we have the reactions. We can move on to different sections of our beam to calculate our shear force and bending moment equations, and then draw the bending moment diagram. So in this beam we have a change in the force here at a change in the loading here in the center, and a change in the loading at B. So we're expecting 2 sections where we need to write bending moments and shear force equations. So for the first section, where we have the value of x can go from 0 meters to 3 meters, where I'm measuring x positive to the right from A. So to calculate the shear forces, first of all, let us draw our free body diagram of the system. And on the right hand side, force applied is RAY. I'm going to draw this pointing upwards, even though I know that the value is minus 5. At the cut, at position X, if I'm going with the shear force rule up on the left, down on the right, I can write my shear force Vx down on the right, and I draw my bending moment anti-clockwise to give myself this kind of deformation to be positive. Finally, for the free body diagram, the last thing to always put on there is the coordinate itself, x. So for the shear force, take sum of the forces in the y direction. Sum of the forces in the y direction, and I have RAY minus Vx equals 0 for equilibrium. Therefore, Vx is equal to RAY. And I know now that RAY, I can substitute the value I've already calculated, is minus 5 kilonewtons. And for the bending moment, I take moments about the point where I'm looking at the moment m of x. And so I have m of x, and this is going anti-clockwise, so it's positive. And then I have RAY multiplied by the lever arm to that point, which is x distance along. This is now going in the clockwise direction, so that is negative. And for equilibrium, that is all equal to 0. So I can rearrange this now. M of x equals RAY multiplied by the lever arm x, and then substitute my value for RAY, which was minus 5 times x. So those are the shear force equation, bending moment equations for the first half of the beam. It's useful as well to calculate what the bending moment will be at the center. So let's calculate m for x equals 3. And my function is minus 5 multiplied by the value of x, which is 3. So it equals minus 15 kilonewton meters. And that's the value we'll use later. So we'll go on now to the right hand side of the beam. So we have, for the right hand side, that is where x is between 3 meters and 6 meters. And I'm going to draw the free body diagram, but this time I'm going to draw the free body diagram from the right hand side. And so I have a reaction at this right hand side, RBY. And for the shear force convention, up on the left, down on the right, I have to draw my shear force V pointing upwards. And again, because I'm making my cut on this left hand side, my moment to keep equilibrium will be going in a clockwise direction. Just to finish this free body diagram, we add the coordinate axes, and we're measuring an x dash from the right hand side. So our shear force is the shear force at a position x dash, and our moment is our moment at a position x dash. So slightly strange using a coordinate system that's not x, but we'll just show how this works through. So for the shear force, again, we calculate the sum of the forces in the y direction, and we have Vx plus Rby is equal to 0. So we can rearrange this for Vx is equal to minus Rby, and now substitute our value for Rby, which we've already calculated. So Vx equals minus 5 kilonewtons. And we'll carry on to calculate the bending moment, try and keep the free body diagram on the screen. So let's take moments about the position x dash, and having a look at our free body diagram, we have mx dash going in a clockwise direction, so negative, and then we have Rby multiplied by the lever arm x dash, and this is going in the anti-clockwise direction, so it's positive, and for equilibrium is equal to 0. And we rearrange this equation now, take the mx minus mx dash to the right hand side, so we end up with mx dash equals Rby multiplied by x dash. And now we substitute our value for Rby, so mx dash equals plus 5 x dash. And before we draw our bending moment diagram, now we have all the functions in place, we're going to calculate our value of the bending moment at the center of the beam. So m, where x dash is equal to 3 meters, is equal to 5 times 3 meters, which equals plus 15 kilonewton meters. So finally we're going to draw our shear force and bending moment diagrams. So shear force and bending moment diagrams. And as we've done with most of the problems, let's draw the situation, remind ourselves that we had RBY, and you might even want to draw on this final that we had -5, +5, and in the center 30 kilonewton meters. Written as positive because the arrow is telling us that it's going anti-clockwise. And then we draw some straight lines down to where we're expecting to get changes in our shear force diagram. We've already seen we do because we've previously calculated the equations and the values at those points. And then finally one at the right hand side, and let's put some x-axes in place. So for the shear force and for the bending moment, so this is x in meters, x in meters. For the shear force diagram, going up as positive, so that's V over x in kilonewtons. And for the moment, as we've done for all the other problems, because we're choosing tension to be on the, to draw bending moments on the tension face, we need to draw our axes pointing downwards, and the units are kilonewton meters. Now we go back to our shear force functions, and for this right hand side we had shear force was a constant -5 kilonewtons, and likewise for the left hand side we had a -5 kilonewtons. So drawing our shear force diagram now, just shading it in, label it up, -5, -5, and we see at the center that the point moment has made no difference whatsoever to the shear force diagram. Now we're going to go on to write the bending moment, and if we look for our left hand side, our bending moment function was a negative slope in x and reaching a maximum value of -15 at the center. So a negative slope in x needs to go upwards in this case, and on the right hand side we had a positive slope in x dash. X dash, remember, was going in this direction, so we draw x dash, and then finally shading the diagram. And label up key values, so 0 and 0 at the ends, and we had -15 coming from the left hand side and +15 if we came from the right hand side. So we have a jump in the bending moment diagram, and this jump is equal to the 30 kilonewton meters of the applied moment. So whenever we apply a point moment, we will get a jump in the bending moment function. One final thing to note, we have this bending moment diagram like this, and it's this is one of the cases where it's really useful to understand what is happening with the shape, the deflected shape of the beam. So if this black line here is the original shape, we know at the left hand side we have a support condition and that the beam cannot move up or down. We know at the right hand side we have a support condition, beam cannot move upside down, and as a result of the applied clockwise moment at the center, we expect our beam to twist round. And using this bit of information, we can then draw the sketch of the deflected shape. And then we can see that we have tension at the top of this part of the beam, tension at the bottom of this part of the beam, and by drawing our bending moments on the tension side, we can check from our intuition on how the beam deflects whether the bending moment has been drawn correctly.